And I will tell you a little bit about nanowire growth using a catalyst particle. But let me give a disclaimer at the beginning itself that this catalyst, the word usage of the word catalyst might be a little bit unconventional in this context, and I will tell you a little bit more as we go along. So this is going to be about nanowire growth using a catalyst, as I mentioned. And the work was done, now I'm in Karlsruher Institute of Technology, but this work was done while I was at Cologne University. And let me first tell you what nanowires are, and then I will tell you what semiconductors are, and then we will go about growth of nanowire semiconductors, and then I will give you a little bit in-depth details about like our studies recently. Okay, so nanowires are like nano wires. The thickness of the nanowires are typically tens or hundred of like nanometers, and it's usually much longer than the length is much bigger than the width of these materials. And so these wires obviously are very tiny, and there are a lot of material systems that you can grow as nanowires, including metals and semiconductors and so on. And as you know, semiconductors, like the most popular semiconductors are silicon and germanium. Silicon is what we use in a lot of our electronic applications like laptops and phones and so on. This is an excellent semiconductor, but it has a few limitations. And one of that is that it cannot be used for any application where you want light to be emitted. In such cases, like you can use compound semiconductors, which are, say, for example, if you combine a group 3 element to a group 5 element, there are chances that you can get a direct bandgap semiconductor, and that can give you light. And like for if you want to make LED bulbs or laser pointers and so on, what you would use is a compound semiconductor. And why are nanowires interesting is, as I told you initially, like most nanostructures, including nanowires, are like much smaller. And so you can have like arrays of nanowires replacing the current, say, silicon technology or like so on, where like things are much more miniaturized for the same sort of semiconductor processing. A very interesting aspect about nanowires is that because the surface to volume ratio is so high and surface energy is a very important aspect of this, we can tune things in such a way that some metastable crystal phases are also possible to achieve while growing nanowires. And it is also like if you are trying to grow compound semiconductors as nanowires, then it is more easy to integrate that onto a silicon substrate or a silicon nanowire segment, much more easier than planar growth of compound materials on compound semiconductor materials directly on silicon. And you can control the 3D shape of these materials, and these materials have a very large surface to volume ratio. Now, how are nanowires synthesized? So nanowires are usually synthesized by a technique called vapor liquid solid, which is basically that the precursors or whatever materials that you are supplying is supplied in the vapor phase. It dissolves in a liquid particle, and the liquid particle gets supersaturated and it starts precipitating out a solid material out of this. This is called a vapor liquid solid route. If we are trying to like grow, say for example, a gallium arsenide material, then we supply a gallium precursor and an arsenic precursor in the gaseous phase or the vapor phase. And then we use gold as a catalyst, or at least we call it a catalyst. And we heat the system and play with the parameters to get these nanowires. Now, so in conventional, or like the definition of catalyst is basically that you have to reduce the activation energy for a reaction to happen, right? But that need not necessarily be the case for catalysts used for nanowires. Nanowire catalysis might just be that there are particles, either solid or liquid, very often liquid, liquid particles which collect the materials and then get supersaturated, and on supersaturation precipitates out the solid. So but the convention in nanowire community is to call this particle a catalyst, even if it's just a material sink. The role and like how this is working is still like debatable, but that's how it's called. So usually when people are trying to grow nanowires, we take a substrate, put gold particles or any metal particles which are appropriate for the synthesis of those particular nanowire systems, put it into a closed box and play with the parameters and like introduce your gases and heat it, and you get out, if your conditions are correct, like you get out a sample with nanowires. But you don't really get to see what is happening exactly inside the reactor because it's almost like a black box. So there are a lot of questions related to the mechanism of nanowire growth because most of the time we are not able to see how the growth is happening. For example, the nanowire growth is supposed to or like expected to happen layer after layer after layer. And whether this layer propagation is instantaneous or whether it is a slow process, all those things, especially for compound nanowires, is not very well studied. So if we are able to grow the nanowires in a system where you can also look at these wires, then you can learn a lot of things about this. This material system and about the mechanism. And hence we use an environmental TEM to grow nanowires and watch the wires as they grow. So this is just a schematic of the system that we had, where there is a system or where there's a section for mixing the gases to like required at required temperature, like the sources should be at the required temperature and pressure and controlled flows going into the microscope. We have a Hitachi environmental TEM, and we view this on a screen and look when the wire is growing. Now, the holder that we use is having two tubes at the back end of the holder through which the gases are supplied, and we can like put it into the TEM, and at the front of it there is a locally heated MEMS chip. This keeps the heated portion very small compared to, say, if you're using a furnace heater in a furnace heater of like a kind of TEM holder, then there's a very large region which is being heated, and that is going to give a very large drift while you're doing the experiments when you're changing the temperature. But if you have these MEMS sort of like design, the heating is very local, and hence the drift at each temperature is very minimal. So when you change from one temperature to another temperature, it might take maybe half a minute or so to stabilize, but once, actually not even half a minute, you see it like in maybe like 2-3 seconds, you see a drift and then it stabilizes. So it's very easier to look at any in-situ heating experiments with this kind of system. And the total IR radiation that you get due to the sample heating is also much smaller, and which is why we can get some of the results that I will show you in the following few slides. So this MEMS heating system, if you look at a closer look, it has this coil, and there are regions of the sample that you can, thin regions of like this chip where we can monitor the growth. And we are looking at the growth, and we can see, let us look at a few different examples. So this is an example where we had a gold particle. We supplied the gallium precursor, and now there is a gold gallium liquid alloy formed. And we are keeping on supplying the gallium precursor and the arsenic precursor, and let's see what happens. So you see there's like one chunk which started growing, and now it's like becoming a nanowire. And let us look at another example. Here again, you see the nanowire like growing, and you see that the nanowire is growing one layer after another. And you can see that there are two different crystal structures also. Like this is in a woodside phase, and this is actually a England phase that you see. Now, if you look at, let's look at a little bit more scientific results that we can obtain. Now, as I mentioned, like this catalyst particle, which is sitting at the top of the nanowire, is a very interesting thing. And like we can study the composition of the catalyst particle while the nanowire is growing. So this is like the first time that such a in situ study is being done. And what we do is we do like energy dispersive X-ray spectroscopy or EDX in the TEM mode, but we condense the beam to the front of this particle and uh, because the nanowire is growing, that means this front part is also like moving, and we manually like move the sample stage in such a way that the beam is always positioned in the front end. And then we take an EDX spectrum and it looks somewhat like this. Here we are using gold catalyst and a gallium arsenide nanowire, and there is silicon nitride substrate. And we can look at the percentage of gallium which has mixed with the gold to form this liquid gallium, gold gallium alloy. We can look at a few different nanowires at the same condition and compare the gallium concentration, and we see that it is like pretty much the same or like very comparable values across different nanowires, while we are since we are keeping the reaction conditions the same. It's the same growth. Now you see, like we also measured the arsenic concentration in the catalyst particle, and we see there's like very, very little arsenic inside the catalyst. Now, this is not very surprising if you just look at how materials mixes. We can see that the arsenic is anyway like expected to have very little solubility inside a gold catalyst. So this is not surprising. And we studied this the arsenic concentration and like the gallium concentration as a function of different reactor conditions, but I'm not going into the details, but you can find the details in this paper if you're interested. Now, the point I want to you to like keep in mind from here is that the arsenic concentration is very, very small. And we are trying to grow a gallium arsenide wire, and these things have to go into the catalyst nanoparticle before forming the wire. Now, if arsenic concentration is very, very low and gallium is like say 1/3 of the material, does this mean that gallium and arsenic controls the layer growth process very differently? This is what we want to study next. And we see here that like what I showed initially earlier, the layer growth is not an instantaneous process, and we want to see what aspects the gallium and arsenic are controlling in this layer growth process. So we try to like analyze and measure two different steps inside this layer growth process. One is called the layer completion or the step flow time, which is basically the time from the start of a layer to the ending of a layer. Okay. And the next one is called the incubation time, or you can just call it the waiting time, which is once a layer is formed, how much time does it take for the new layer to start? That is called the incubation time. In at least we call it the incubation time. Now, what we want to study is to see what determines these two like parts of the nanowire growth. And we see here that with increasing arsine pressure, the layer completion time or the step flow time decreases very drastically. Okay. And if we look at the incubation time, there's a small increase, but it's not much. If we look at the gallium, if we keep the arsine flux fixed and change the gallium precursor flux, we see that initially the incubation time rapidly decreases, and after that it sort of like becomes not very sensitive. And the step flow time, except at extremely low trimethyl gallium fluxes, is rather a constant. Now, what does this mean? This means that the nucleation of a new layer is triggered by the gallium supply. But for a gallium arsenide to form, there is not just gallium, we also need some arsenic. But the arsenic concentration in the catalyst is very, very small. So how fast each layer finishes is determined by how much arsenic is supplied or how much arsenic is there in the catalyst particle. So the nucleation is Nucleation of a new layer is limited by the gallium supersaturation, but how fast each layer finishes is determined by the arsenic. Now, is this something which is specific only to gallium arsenide, or is this a universal phenomena? So we expect this to be sort of like applicable to a whole lot of different material systems, because here the point is that arsenic concentration in the catalyst is very, very small. And that is why we see this layer completion to be limited by the arsenic. And there are many different systems, like most 3,5 materials or like 2,6 materials, they have this the group 5 or the group 6 material has very limited solubility in the catalyst metal, which means that the nucleation is again going to be limited by the group 2 or the group 3 metal, but the layer completion is going to be limited by the group 5 element. Group 5 or group 6 element. And the next part of the talk, I will tell you about a little bit about vapor solid growth, which means that, so earlier we had vapor liquid solid growth, where the precursors are given in the supplied in the liquid phase. It dissolves in a precursors are like supplied in the vapor phase. It dissolves in a liquid particle, and on supersaturation, it precipitates as a solid. But here we have a vapor solid mechanism, which is that the catalyst is in a solid phase. So the precursor is coming from the vapor, can go into the solid, or at least can be on the surface of the solid, and then it supersaturates and precipitates out the solid nanowire. And why is vapor solid interesting? So vapor solid is interesting because if you want to make, say, a heterostructure, and if you want, say, a gallium phosphide material followed by a gallium arsenide material, then you want that switching to be abrupt in most cases. And if that is the case, if your catalyst particle is liquid and if it is having a lot of these precursors already dissolved in it, even if you change the gas phase precursor, it will take a long time before this catalyst gets depleted and incorporated into the nanowire. And this is called the reservoir effect. So when the reservoir of like materials is smaller, which will be the case when you're having a solid catalyst, because in a solid, the solubility is going to be like much lower than a liquid particle. And so you can achieve like a abrupt switching in vapor solid. And our motivation for studying vapor solid growth was to understand a little bit in more detail about like the nanowire growth mechanism. There are different studies which people have made about vapor solid growth also, but all those were on elemental nanowires. Actually, they were all studying silicon nanowires. But just before we saw that, like we were trying to grow a compound nanowire, gallium arsenide compound nanowire, using vapor liquid solid, and there itself we see that the dynamics or the kinetics are very different from that of a elemental nanowire. So we wanted to study and see how vapor solid growth is going to affect the compound nanowire growth. And we want to see, importantly, whether the growth rate is going to change when you're having a vapor solid growth. And we want to see like how the different two steps, the waiting period and the layer growth step, are whether they're going to be affected differently. So let us look at vapor solid growth experiment. So initially we started with a vapor liquid solid growth. We decrease the temperature in steps. So we started from here and we are like cooling in steps and looking at the kinetics at each of these temperature. And around like at around like 320 degrees Celsius, the temperature, when the temperature was around 320 degrees Celsius, the particle solidified, and then we have like vapor solid growth in the rest of the temperatures. And in the vapor solid growth, the catalyst obviously is a solid particle. And we can look at the average growth rate when the particle was a solid versus a particle on liquid. So here we have plotted the growth rate as a function of temperature. We see that if we keep on decreasing the temperature, there is like a slight decrease in the growth rate. And once the catalyst has become solid here, which is happening across this blue line, we see that the growth rate decreased slightly, but this is a very marginal decrease. Actually, like if you look at the error bars, it's not even any significant decrease happening. So in the case of a compound nanowire, this shows that it is not necessary that a vapor solid growth has to be orders of magnitude slower than a vapor liquid solid. Now let us look in detail or at the two different parts that we discussed before, the incubation part and the layer completion part. So this graph is slightly confusing. What I have plotted is I'm like cooling and I'm looking at each layer completion as a function of say you can either call it the layer number, or you can this is just progressing one after the other. You can say like the x-axis is almost say like time. So the from 420 to 320, we see that the incubation time and the layer completion time is reasonably like the same. And you see one after the particle solidifies here also, the incubation time and the layer completion time are very similar to that at 320 degrees Celsius where the particle was in a liquid phase. And at slightly lower temperatures we see that there are also like double layer growths which are happening. And this is something which we see in other experiment also. So this is a second example where you see that there are this like double layers which are growing inside this, and this is consistent like for the different experiments that we see. So in the VSS case, or the vapor solid growth, we see that there are often cases where there are multiple layers growing. There are sometimes even like 4 layers growing. But in a vapor liquid solid growth, it is usually one layer after another. So there is definitely a qualitative and quantitative difference among vapor solid and vapor liquid solid. Now, if you look at the numbers of layer completion time, here you can see, you can ignore for now like this 260 degree VSS and just look at the 280 degrees Celsius, but the two cases, the VLS case and the VSS case. And you see that there are instances where there are multiple layers growing at the same time. And if you look at the incubation time, it's just like very comparable to the incubation layer completion and the incubation time. Now both very comparable across the liquid and solid. So if a liquid and solid is very like comparable, this would mean that we normally would expect that the arsenic and the gallium has to diffuse through the catalyst particle and then reach the growth interface. But here we see that through the liquid and through the solid, it is reaching pretty much at the same time, which means that diffusion of the material is not somehow the limiting factor here. It can be that the diffusion through the particle is slow in a solid than a liquid, but that is not at least the rate limiting step. That is why we are seeing the incubation time and the layer completion time to be very comparable across VLS and VSS. So it may be that the particle, like the arsenic, is probably just diffusing through the surface, or maybe because this is a very tiny grain, this just like it makes maybe diffusion much easier. But anyway, we know that the diffusion through this particle is not, through the catalyst particle is not the rate limiting step here. Now that brings me to the end of the talk, and before I summarize, this is our group at like Lund University, like with Kimberly, who's like leading the group, and all of us, some of us working at the environmental TEM and some of us working at in-situ systems. And to summarize, I would like initially we discussed this. Initially, we discussed the measurement of the catalyst composition in situ while the reaction is happening, and this was studied in an environmental TEM. And this was partly possible only because we had this MEMS chip. If it was the furnace holder, then there is way too much IR radiation for using the EDX detector, and we could not have achieved any EDX measurement in that case. And I showed you a little bit about the VLS kinetics and showed how gallium and arsenic, or the group 3 and group 5 precursors, control different aspects of the nanowire growth. I also showed you like vapor solid solid kinetics, and like showed that the growth rate is not not much slower than the vapor liquid phase solid group. Yeah, so that's pretty much what I wanted to tell you, and thank you all for your attention, and thanks for this opportunity. Yeah.